Today, I'm going to talk to you about entropy. Entropy is probably the least understood concept regarding AI that you should know the most about, is how I would frame entropy overall. Starting off with a simple analogy. Imagine an egg cracking, right? We can imagine this very simply. Humpty Dumpty fell off a wall, and then Humpty Dumpty put himself back together again, or couldn't put himself back together again. And so uh, that imagination stretches the imagination, right? The fact of Humpty Dumpty putting himself back together, or people putting this egg back together again, would be a stretch of the imagination. The egg cracking, very easy. We can understand that. And that happens in physics all around us. An egg uncracking itself would defy the laws of physics overall, right? We can't, it's not something that's easily even imagined. And then, so within that, the reasons for that are due to entropy. The reason why an egg only cracks one way is because of entropy overall and how that interacts within our system, the system being our universe and the Earth itself as a whole. And we'll get into that when we dive deeper into exactly what entropy is. So, first of all, let's start at the very high level. What is entropy? In the simplest terms, entropy is a measure of the number of possible arrangements that a system can have. Think of it as the universe's tendency towards spreading energy and matter out as much as possible. So, number of possible arrangements and a system. These are the two critical components within this. And number of possible arrangements means just number of possibilities. We'll dive deeper into this, and a system can be anything, and there's multiple definitions for what a system is, and the system and the design of the system itself can change how entropy interacts and formed in that environment. So why should we care about this? Why should you care about entropy overall? Well, it governs essentially everything around us, from the melting of ice to the burning of stars. It dictates the flow of time itself, and it even has implications for the ultimate fate of the universe itself. Understanding entropy gives us a powerful lens through which to view the entire world around us. Just as you can understand the concept of energy and concepts related to energy, like energy conservation, etc., entropy plays these same laws and these same rules. We'll dive deeper into this, but it literally is a part of and a fabric of the laws of thermodynamics. Diving into entropy and disorder. Oftentimes, you might have heard entropy described as a measure of disorder, and while that's not entirely wrong, it can be misleading. It's better to think of entropy as a measure of how spread out energy and matter are, or the number of possible arrangements for a given system to have its energy. And that number of possible arrangements is the important detail, and we'll dive deeper into exactly what that means. Starting with microstates versus macrostates. So, to understand this better, let's introduce two terms: microstates and macrostates. Imagine a box of gas. A macrostate is a general description of the box, like the temperature is 25 degrees Celsius and the pressure is 1 atmosphere. Whereas a microstate is a specific arrangement of every single gas molecule in that box, where each molecule is and how fast it's moving. Many different microstates can correspond to the same macrostate. So the more microstates that correspond to a macrostate, the higher the entropy within that particular system. Looking at this through an analogy of expected distribution and energy. So if we flip coins, right, we flip a coin, heads or tails, and let's say that we flip it 32 times. According to expected distribution, we can expect, generally speaking, that it's going to fall between, we'll get heads between like 12 and 22 of the, more like 14 to 18 of those times and in a very narrow band, right? And we can predict like with more than 50%, like almost 60, more than 60% probability that it's going to be in that range, like 14 to 18 very specifically, right? As to the number of heads when we're flipping it 32 times. There's chances and outliers that we could only hit heads 8 times, or we could only hit, or we could hit heads up to like 24 times. And those would be within the outlier distribution of the 32 coin flips, but going off of expected distribution, our expected distribution falls right in the center. And this ties directly into entropy. Giving you another example of entropy in the real world, here's an example of paint mixing. And then in this example, this is an example of entropy increasing within a system, right? So you add the green paint to the white paint, and then when it starts off, you have a little dollop of green, and then essentially this shape, this system can be anything at this point, right? As you're pouring in the green into the white, the entropy is very high in the system. Uncertainty is very high. Is it going to be white? Is it going to be green? Is it going to be some mixture? How much green is going to be poured into there? But as you mix the paint and as the two colors come together, there's uncertainty decreases within that environment, right? So you have essentially the paint comes together, and then you have more and more known decisions, but within that, more decisions that could have been made within the system overall. And then tying this also very specifically to thermodynamics and regards towards heat transfer. So heat always transfers from hot to cold, and then always seeks to have an equilibrium between the two, right? So heat will transfer, or energy will transfer from hot to cold until the cold environment and the hot environment balance out as far as energy, and then you won't have any more energy transfer anymore. And that's just, pure physics. And then one important caveat to make within this before we move on is that people are open systems and not closed systems. So all of this relates to systems, and everything that we've been talking about, heat transfer, the increasing of entropy within an environment, expected distribution, all of these operate within closed systems, and there are rules for closed systems. And then we can't equate these to the human body, for example, because the human body is a closed system. Earth is a closed, or is an open system, meaning that there's systems that exist outside of the system that can disperse energy too, right? So when we sweat, we evaporate, and then we have sweat evaporation, we have breathing evaporation, convection comes off of our body from heat, we expel radiation into the environment, we have conduction through different processes, and then we essentially expel energy out of our environments. So we're not a closed system overall. And then tying this very formally to the second law of thermodynamics. The second law of thermodynamics states that the total entropy of a closed system can never decrease over time. It can remain constant for reversible processes or increase for irreversible processes. But a closed system is one that doesn't exchange energy or matter with its surroundings. So again, the body wouldn't be a closed system. Earth wouldn't be a closed system. The universe is a unique example of one system that falls in between these definitions, as to our current understanding, in that it's not a closed system and it's not a open system. It's a system that is not attached to any other system, which makes it kind of unique within in that framing. But a computer would be a closed system, like a warehouse, a factory would be a closed system. Moving on from general entropy, and then tying this very specifically to computer science and information entropy, this leads us to the concept of Shannon entropy. And entropy isn't just a concept within physics, it also plays a crucial role in information theory. So information theory, also known as Shannon entropy, measures the uncertainty or randomness in a message or a specific set of data. So a highly predictable message has low entropy, while a completely random message has high entropy. And then so Shannon entropy deals with entropy of systems and digital systems and computer systems very specifically. And so within this, we can measure entropy as uncertainty. So going back to that coin flip example, if the coin is fair, the outcome is uncertain, whether it will be heads or tails, and the entropy is high. If the coin is biased and it always lands on heads, then the outcome is certain and the entropy is low. Meet Claude. And so a lot of you might be familiar with Claude, the LLM model. And so there's a very specific reason why Claude has its name Claude that you might not be familiar with. Claude is very specifically named after Claude Shannon, who is the mathematician behind Shannon entropy and information theory. And so he was a mathematician and an engineer. And he's considered essentially the father of information theory. And he developed a mathematical way to measure information, which he called information entropy. And so, what is information entropy? Information entropy measures the uncertainty or the surprise associated with a message or an event. It tells us how much information we gain on average when we receive a message or observe an event. So high entropy equals more uncertainty equals more information gained from that. Whereas low entropy means less uncertainty, means that we gain less information from that particular event. So if we are trying to learn chess, if we watch a chess match for the first time, we're going to gain much more information from watching that first chess match than we will from watching the 1000th chess match. The amount of information that we gain will decrease over time, right? We'll have less and less uncertainty. And so going back to the coin flip examples. So imagine the coin flip and a fair coin flip. So you have 50% chance of heads and 50% chance of tails. In this situation, the outcome is very uncertain. It's 50-50 either way. And so when the coin lands, we gain a significant amount of information. We learn whether it's heads or tails. And then so in this situation, the entropy is very high, right? We don't know what the outcome is going to be up front. And then so if we look at a chart, if I flip the coin and I say, is it heads or tails? We don't know what the outcome will be, right? But if I give you a chart and it says tails very specifically, and you know, that changes the outcome, right? So having that information is very valuable in this instance. It's the most valuable piece of information that we could obtain from this particular example, right? But we can also flip this on its head and look at the biased coin flip. So let's imagine a coin being flipped by Two-Face from Batman. And there's 99% chance that it lands on heads and then like 1% chance, not even, that it lands on tails. And then so this outcome is almost certain. It's probably going to be heads. Even Two-Face knows it's going to be heads. And then so when the coin lands, we gain very little information. Everyone in the room already knew that it was going to be heads. So this is a low entropy situation. Like it doesn't shock anyone. It doesn't change any events when that coin gets flipped. And then when it comes up heads, it's like, yeah, like that's how it's going to be, right? Like it's biased and weighted that way already. And then within this, so we've been looking at this concept of broad entropy, right? And the concept of coin flips and biased versus unbiased coin flips. But we can look this down. Most problems don't fit in that neat little box. And we see this more and more with regards towards information theory and trying to move forward and progress LLM models, right? This kind of like, let's break down the problem into incremental steps. And then so within that, when we do that, when we break down that problem into incremental steps, we're incrementally reducing the entropy of the situation. So framing this as an example of a number guessing game, if the number is between 1 and 50, entropy is very high in that situation, right? It could be one of 50 different situations. If you guess 25 and then I say it's too high, entropy is all of a sudden cut by 50%. We have cut entropy more than any other situation, and that's important too, right? That first involution, that first time that we cut entropy, we cut it by 50%. And then so we're never going to cut it by 50% again. It's always, so we can incrementally reduce entropy, but it's also important to remember this concept that we can't ever do it like the same or more, right? We can't go from like, we're going to incrementally reduce entropy 50% on the first involution and then 60% on the second. It won't, like that's defies laws of physics, no matter how you're defining the laws of physics. And so that leads us to this chart, right? The more you know, the less you can learn. And then so there's a certain point where you're doing this, where you have increasing returns. And then you hit that point of diminishing returns. And that point of diminishing returns is, generally speaking, when you've exhausted like more than half of the known probabilities of the data set. Then you start getting into diminishing returns, and then you hit the point of maximum yield, where essentially it costs more energy to extract and remove the entropy that's remaining and to find the more positive outcomes than it is just a random guess from there at that point. And then at that point, you've hit your maximum yields. And then within this, it's important to note and to bring this back into actual real-world concepts. So Shannon entropy is measured in bits. Shannon, he very specifically measured it in bits, like bits and bytes. So bits of information. 1 bit represents the amount of information needed to reduce uncertainty by half. And then so when we're talking about that 50% threshold, that's this concept, right? We need a way to define that mathematically for a lot of different reasons. And then so that's what a bit is in this instance. So in our coin flip example, each flip, if the coin is fair, provides us about 1 bit of information. And then within this, so we want to define this very specifically and define bits, so we can do this. So we can create the Shannon entropy equation. And this is the formula for Shannon entropy, and it looks complicated, but the idea is very simple. So you start off with your final entropy state, right? This is the entropy of your information source on the left, and then from there, what you're trying to calculate is the probability of each outcome. And then so that's all you're doing. Right, so you do your probability of each outcome, and then each involution is that log squared. Right, you're doing the involutions against themselves, and then that's where we get diminishing returns and all of these equations that come out. Like this comes out of the equation that we're looking at here, right? And then so the formula calculates a weighted average of the information content of each outcome. And then so again, every involution that you do is going to change this equation. If you're finding more certainty within the equation, you're going to find less certainty the next time that you do it. And so very common uses for Shannon entropy. All of this has been around for a long time. It's not new, right? We use it in data compression, cryptography, communication, and machine learning. It's the building blocks of lots of these different things. You wouldn't be able to create zip files without Shannon entropy. Cryptography wouldn't exist without Shannon entropy. Understanding how cell phones, the internet, talking to you via this video, all of that, understanding the limits of communication channels, all boils down to Shannon entropy, and then building out decision trees and lots of algorithms all boil down to Shannon entropy. So let's take this a step further and look at what this means in digital space and kind of where we're at with this at the moment within digital spaces, right? So this is an example of Hamming distance. And what I want to highlight and point out to you is that Shannon entropy with it is in very specifically with regards towards information-based systems, so like digital systems and computer systems, but within this, these systems still follow the laws of physics and have laws of physics within themselves and can be considered systems in of themselves, right? So when it comes to Shannon entropy, at the very least, these systems are no different than the Earth, than the universe, than anything else. And then so within that, they have their own rules, and then we can utilize entropy and we can measure entropy within these environments, right? And so we can use it to measure distance within a digital environment, for example. And then by measuring that distance, we can do different things with that. We can create coordinates, shapes, etc. And that's where you get having distance from. We can also utilize this more specifically for like signals. So this relates to like more data that you would be used to, like bits, so zeros and ones, and very binary. But before the data gets to binary, let's say it's a sound wave or something along those lines, like a signal. Via Fourier transforms, we can transform that signal into data, like into bits, right? And then we know all of this, and we can do all of this via the Shannon entropy equation. So essentially, this equation shows us that anything in like the digital space or this digital realm, these signals, sound waves, light waves, etc., we can transform them into other types of data, basically. And taking this a step further, here's an example for you, just like crystallizing this very clear. Here's the shape of an echo, and echo being like hello, 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 and then so if I do and I measure an echo within a closed system, this is the shape of it that occurs, right? And then so it's an actual shape, and we can see that the shape stabilizes, right? And that's where like how the echo is, and how it's able to maintain its form essentially, and then we see that it does increase in frequency here, right? Like so once it maintains that shape, hello, 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 you know, like it's the frequency is going up as a result of the entropy, and we can directly measure this within a system. And taking this a step further, we can directly measure this entropy within digital systems. And we can do this in lots of different ways now, and in lots of different spaces. We can essentially like utilize and prove out and utilize entropy as like digital eyes, and for lots of different situations that you wouldn't think of possible, right? We can utilize entropy of a data set to create, know the geometric shape of the data set overall. These types of concepts, all of this boils back down to entropy within the system. And then so within this, like the coolest part of this, and it's the part that like even people that dive into this are still like, this is the first part that they struggle with, because it's so mind-blowing when you dive into this, right? But so I just want to highlight and end this video here with this concept that digital spaces can be different system types. And then so going back to the top, remember there's different systems. So you have isolated systems, closed systems, and open systems. Isolated system being what we assume that the universe is. And so the universe being a system that is not necessarily a closed system or an open system, but is not connected to any other system. And then so within that, it has unique rules, right? And then so within our system, heat only transfers one way, and our system, it essentially goes towards equilibrium, right? When you have hot or cold, if you have too hot, it's always going to transfer to the cold, and then it's always going to seek equilibrium. They both the transfers only one direction, period, right? And then so that's what leads us to believe that the universe is an isolated system, because of the fact that heat transfer operates this way within the universe. Whereas if you take a completely closed system, heat transfer within the system itself, within the closed system itself, heat can transfer around within the system, but cold can only move one way within that system, which is very important, right? That's a very important distinction from an isolated system. Very important distinction from our universe, right? You can have heat pumping into this closed system, which is going to cool air will only move in one direction. Whereas in an open system is the exact opposite, or different behavior, where you have hot and cold being able to move in both directions within the system overall. But within this, the important and cool part to me overall within this is that you can reshape systems and environments, and change the behavior of these properties within these environments. So this is a breakdown of systems of digital spaces between isolated, closed, and open, but we can also break down systems between hyperbolic, Euclidean, and spherical, for example, and then within that, and fractal. And then within that, we'll notice different entropy properties within those different systems. And then so we have different levers, like so many levers that we can pull with regards towards system entropy in digital systems that we don't have within real world systems. And once you start exploring that, cool things happen. Like if you see my videos where I'm like doing things like creating like a pyramid and connecting it to a sphere, etc. The reason why I'm doing all of those things is very simplistically playing around with the digital environments and the digital entropy within the environments, and these systems, isolated versus closed versus open, right? And an isolated system is going to function differently than a closed system, which is going to function differently than a connected system or an open system. And then within that, breaking it down further, a sphere is going to operate differently than a pyramid when it comes to entropy compression and agent compression. I can also do different things. So within a digital environment, to me, an isolated system is never truly an isolated system within a digital environment. I can pump energy out of the system. I can pump energy or entropy into the system. So to what does it connect to? I don't know. An undefined digital environment. But it's not. It's Schrodinger's environment, Schrodinger's system, right? Which is why digital systems are so fascinating to me within this. It's an isolated system, it's a closed system, it's an open system, it's a connected system, and it can be all of those things, and I can define them, and I define the systems, and then when I define the system, the digital system, that's when the laws of physics change within the system by that definition, which is super cool seeing that sometimes operate within experiments as to how this works. And then so within that, I mean, what that shows you at the end of the day is that everything is bound by physics and by the laws of physics, even though the laws of physics can change depending on the system and the environment. If you like this type of content, please like and subscribe. Thank you very much.